Hello, everyone. This talk is going to be about our stock paper, Lifting Some Squares Lower Bounds. I'm Siddhant, and this talk is based on joint work with Prasad Raghavendra and Jeff Shu. I will be giving the first half of this talk, and Jeff will give the second half. So consider the following simple model. So you have a random matrix M, which is symmetric, and every entry has an independently sampled Gaussian. And let's define this function opt of M to be the value of the max cut in the complete graph with weights given by the entries of this matrix. So turns out that this quantity, opt of M, is actually an extremely well-studied quantity. And the exact value of this quantity was predicted by Parisi to be something like 3/4 times the maximum eigenvalue of this matrix. And eventually this prediction was rigorously proven by Talleyrand. With this as a setup, now let's turn our attention to the algorithmic question at hand. So now M is a matrix. It's either a Gaussian matrix or it's the Laplacian matrix of a random deregular graph. So you should just keep in mind that M is some sort of random matrix. And now we want to certify upper bounds on the value of opt of M when given M as input. So in the latter case, when M is a Laplacian of a random regular graph, we simply want to certify upper bounds on the value of the maximum cut in the underlying graph. So one simple way you can certify an upper bound is, well, you compute the maximum eigenvalue of the matrix M, and you notice that this vector X, which you're maximizing over, always has norm root n. So the maximum eigenvalue of M times n is always an upper bound on opt of M. So you can compute that number and output it. However, based on a discussion on an earlier slide, when M is, say, a Gaussian matrix, there is a gap between what opt of M is and what the eigenvalue-based upper bound is. Now, this gap that exists for the eigenvalue-based algorithm, one could ask whether this gap is actually something inherent to all polynomial time algorithms, or whether it might be possible to come with other polynomial time algorithms that either reduce the gap or even possibly close it. But we believe that the spectral algorithm is actually sort of the best thing you can do. And indeed, this gap is inherent to all polytime algorithms. And our results can be seen as some sort of a partial confirmation to this belief. So to talk about what we mean by partial confirmation to this belief, I'm now going to give you all a sneak peek of the sum of squares hierarchy. So for now, you should think of the sum of squares hierarchy as being a sequence of increasingly powerful algorithms. And what each algorithm does is it takes an M and it outputs an upper bound on opt of M. And since the sequence of algorithms is increasingly powerful, okay, first of all, every level of the sum of squares hierarchy certifies a better upper bound in the spectral algorithm. And as you increase this D parameter, your upper bound gets better and better. And actually, when it finally hits 2n, it solves the problem of computing opt exactly. And one thing that I should mention is that SOS D of M can be computed in n to the order D time. So in particular, if D is a constant, you can compute this number SOS D of M in polynomial time. Now, this sum of squares algorithm, one may ask, why is it a good idea to study the performance of sum of squares algorithm in certifying upper bounds on opt? Well, it's because it's an algorithm that captures many known algorithms for certifying upper bounds. It's optimal for all constraint satisfaction problems in the worst case, if you assume the unique games conjecture. It captures the best algorithm for sparsest cut. It also captures the best known algorithms for a wide range of average case problems, such as refutation of random CSPs, the planet-clique problem, tensor PCA, and also several machine learning problems. So now let's survey the past work on understanding the performance of sum squares and certifying values, upper bounds on opt. So the first in this line would be a paper of Motonari-Sen, which shows that the degree-2 sum squares relaxation does not beat the eigenvalue-based upper bound when M is a Gaussian matrix or Laplacian of a random deregular graph. the two cases that we consider. And later, Bandera, Kuniski, and Wine investigated this question more, and using some non-rigorous heuristics, this particular heuristic known as pseudo-calibration that you'll see more about later in this talk, they proved that actually from this heuristic, even n divided by log n degree sum squares would not be able to beat the eigenvalue-based upper bound by much when M is a Gaussian matrix. And I just want to point out that n over log n random sum squares is actually an exponential time algorithm. So this prediction is a very strong prediction. And our result can be seen as sort of bridging this gap between what is rigorously known and what is predicted by, or making an attempt to bridge this gap by slightly boosting the rigorously known results to saying that even degree-4 sum squares lower algorithm does not beat the eigenvalue-based certification algorithm for the cases when M is a Gaussian matrix and M is a Laplacian of a random deregular graph. And I should point out that actually in a concurrent and independent work, Kuniski and Bandera independently showed the same result that we did for when M is a Gaussian matrix. Okay, so now we're going to talk about a common theme that ties the problems of when M is a Gaussian matrix and when M is a random deregular graph together. So in both of these cases, the eigenvalues roughly satisfy what is known as a semicircle distribution. And the main consequence of satisfying the semicircle distribution that we care about is that if you look at a tiny sliver, namely between whatever the maximum eigenvalue of M is, and some numbers slightly smaller than the maximum eigenvalue of M, let's say 0.99999 times the max eigenvalue of M, there's actually going to be many eigenvalues in that range as a consequence of the semicircle distribution. In particular, we care to deduce that there's at least n to the power 0.99 eigenvalues in that interval. And actually, the way we prove that the degree-4 sum squares algorithm does not beat the eigenvalue-based refutation is we actually prove in some sense that the degree-4 sum squares thinks that there is a Boolean vector sitting in the top n to the 0.99 eigenspace. And actually, it's worth noting that the top n to the 0.99 eigenspace is some sort of random subspace. When M is a Gaussian matrix, it is literally a uniformly random subspace. When M is the Laplacian random deregular graph, okay, it's some kind of random subspace. It's not uniformly random, but it's random enough for our purposes. So this motivates formally defining the problem that we will call subspace Boolean vector. So in this problem, you're given an n to the power 0.99 dimensional subspace V. Let's say V is a random subspace. And we want to prove that there's no Boolean vector close to this random subspace. Actually, more concretely, you should consider the polynomial system where you're looking for an x. X has to be a plus minus 1 valued vector. And the projection of x on the subspace is large, is very close to its actual norm n. And actually, it's not that hard to show that with high probability, this system that's written in the bottom half of the slide is going to be infeasible. The thing is, degree-4 sum of squares fails to prove that the system is infeasible. So in some sense, it thinks the system is feasible and that there is actually like a Boolean vector with very large projection onto the subspace. So now let me concretely say what it means for degree D sum of squares to think that a certain system is infeasible. So the way the degree D sum of squares algorithm would try to prove that the above system is infeasible is by writing this inequality, namely the projection of V is at least 0.999 times n as a sum of squares. So in particular, if you want to show that there's no x satisfying this inequality, then you'd like to show that for every x, the square form is at most 0.99999 times n. And this is equivalent to showing that a certain polynomial is non-negative. And the way it tries to give a certificate that this polynomial is non-negative is by producing some other polynomials, q1 to qm, such that q1 squared plus q2 squared all the way up to qm squared is exactly equal to this polynomial that we want to show as non-negative. And it's worth noting that these qi's can be found in n to the order d time if they actually exist. Okay, but recall that the thing that we wanted to prove was no such polynomials exist, at least when d is equal to 4. So towards doing this, we introduce the dual viewpoint. So towards introducing the dual viewpoint, I'm going to define what a pseudo-expectation operator is. So pseudo-expectation operator, one should think of as being some sort of a relaxation of an expectation operator. So the pseudo-expectation operator is defined on degree d polynomials. It's a linear function that maps degree d polynomials to real numbers. And now, just like a real expectation is linear, just like a real expectation, when you simply plug in the constant polynomial 1, it should output 1. And also, just like a real expectation, when you feed it the square of a polynomial, where a polynomial has degree at most d over 2, it should give you a non-negative number. And with that, I've defined what a valid degree d pseudo expectation is. So now, actually, in order to show that the program downstairs has no degree d sum of squares proof, by some sort of duality, it suffices to show that the program in the upper half of the slide is actually a feasible program. And the program is the following. You basically want to find a pseudo expectation operator that is a degree d pseudo expectation, such that pseudo expectation of xi squared is 1 and pseudo expectation of the value of projection is at least 0.9999 times n. And the way we achieve this is we give a generic method of translating a degree d pseudo expectation operator for this problem. Sorry, a degree 2 pseudo expectation operator for this problem into a degree 4 pseudo expectation operator. And then we plug in the known results of Montanari and Sen that we cited earlier in the slide, where they actually do construct a degree 2 pseudo expectation operator and obtain a degree 4 pseudo expectation operator. Now, to show that, to show how one constructs a degree 4 pseudo expectation from a degree 2 pseudo expectation, we employ the technique of pseudo calibration. And Jeff is going to tell you more about pseudo calibration in the second half of this talk. Thank you.
Okay, thank you, Sid. For the rest of the talk, I will try to give a brief introduction to pseudo calibration and an overview of our work. Pseudo calibration is first developed in SOS lower bounds for predicting in the work of Block et al. It's a recipe to construct pseudo expectation. So what do we mean by that concretely? It tells us a formula to fill in the entries of the moment matrix accordingly. And by following this procedure, we can somehow get a SOS lower bound if everything works out magically. So even though it's originally intended for SOS lower bounds, it turns out to be also surprisingly powerful as upper bounds as well. Recently, there is this application for community detection in the work by Baines et al. And pseudo calibration as a technique itself also bears some mysterious connections to statistical physics, but we will not get into this today. So let's see, we are trying to get SOS low bounds for refutation problems. However, certification and refutation problems are a little bit tricky to work with. So pseudo calibration actually look at a slightly easier question, the distinguishing problem. Since we know if SOS can certify no Boolean vector in a subspace, then for sure it can also distinguish the following two subspaces, one that contains a Boolean vector and one that does not. So to show a SOS lower bound for the refutation question, it suffices for us to say that SOS fails at the distinguishing problem as well. And towards this end, we need to take a little leap of faith. We like polynomial approximation as a very powerful tool, and it's very tempting for us to think, okay, whether we can approximate SOS by polynomials. And this is not an ungrounded guess, since in many average case problems, we have evidence that SOS can be captured by low-degree polynomials. So for now, let's close our eyes and pretend that this is true. But let's recall what SOS is first. SOS takes in some input. It can be some random subspace, or a Gaussian matrix, or some random Dirichlet graph. And what do we want as output? We want a pseudo expectation, and that's usually given in the form of a moment matrix. So we can think of it as more or less just a matrix value function. And now let's fix some input V, and let's fix a set of vertices S. And we want S to be not too big. And let's ask SOS what the solution looks like on this set of vertices S. SOS will say, yeah, this is just pseudo expectation X to the S. However, if you believe that SOS is captured by low degree polynomial, then this is just a polynomial in the input V. And since this is a polynomial, you can apply Fourier analysis here and write this entry in its Fourier expansion, which is just summing over all Fourier characters, the Fourier coefficients times the characteristic polynomial. And this is exactly the formula that we can follow to fill in the moment matrix. However, before we do this, there's a question we need to answer first. What are these Fourier coefficients? There are some real numbers, but where do we get these? Before we answer this question, let's take a slight detour. Let's recall what we want of our pseudo expectation again. It should be a pseudo expectation functional. Namely, if we ask SOS what it thinks 1 is, we want SOS to say 1 is 1. Also, if we ask SOS what's the square of some low degree polynomial, we want SOS to give us some non-negative real number. And in the problem that we look at, Boolean vector in random subspace, we also want SOS to say that there is a Boolean vector X that lives in the given subspace V. And now we are ready to describe pseudo calibration. Recall that the goal is again to construct pseudo expectation for any random subspace V that's given to us. But it may be hard to work with any random given subspace. Let's say we have the power to pick our favorite input. So we can always pick the subspace V that we already know it has a Boolean vector X. Even though this happens exponentially unlikely, but in these cases, we can always set pseudo expectation to be the moment matrix of the Boolean vector X. And therefore, pseudo calibration dictates that, yeah, you can always learn how to construct pseudo expectation by looking at the subspaces that you like or the input you like. Now let me explain what I mean by learning. Let's consider two distributions here. Let D1 be the uniform distribution over subspaces. So here, D1 is just a distribution that we want to construct pseudo expectation for. And let D5 be the distribution over our favorite subspaces. So in this case, this is just a random subspaces containing a Boolean vector. And we can also think of it as a joint distribution of random subspaces V and Boolean vector X. And pseudo calibration says, okay, you can learn the construction for pseudo expectation by taking samples from your favorite distribution in the following way. Let's fix a Fourier character alpha. You can set the Fourier coefficient of alpha as a Fourier coefficient of alpha in the favorite distribution you like. And this is now just something you can explicitly compute using Fourier inversion formula. So now this is just some real number that we have control of. Okay, why do we want to set our Fourier coefficient that way? Let's fix a character alpha again and set the Fourier coefficient to be identical as the Fourier coefficient under our favorite distribution. This says that for any polynomial f that only use Fourier character alpha, the expectation looks alike under these two distributions. So this tells us that for any polynomial f that only use Fourier character alpha, it cannot distinguish these two distributions. Therefore, if we apply these for characters of all characters of degree at most t, we can also say that there's no degree t polynomial can distinguish these two distributions. Okay, now what do we do next? We can follow this formula and write down a pseudo moment matrix. And if we take the leap of faith that I promised you, that low degree SOS is just doing low degree polynomial. Since we know that all the constraints we want to satisfy are low degree polynomials, and they're already satisfied in the favorite distribution that we can pick, then we know that the pseudo moment we construct will also satisfy those constraints automatically. However, there is one question. We need to prove that the pseudo moment matrix we construct that way is a PST matrix. And if that's the case, we'll automatically have our SOS low bounds. However, it turns out to be a quite difficult task in proving the pseudo calibrated moment matrix to be PSD, because it's actually a random matrix, because this is a random matrix that has some very complicated correlations between entries. And here we introduce a new idea in our work, which we call pseudo-vectorizations. Rather than learning the entries of the pseudo-moment matrix directly, as we do in pseudo-calibration, we learn the vectors for the Gramian decomposition of pseudo-expectation instead. And we call the ground matrix M1. And M1 is clearly PSD because it's a matrix of it's a ground matrix of vectors that we can learn. However, it's not as a lower bound because this is not exactly a moment matrix. What do you mean by that? It does not satisfy certain moment symmetries. Let's look at the matrix entry corresponding to pseudo expectation xi, xj, sk. So this appears in the entry I, jk and ij, k. However, the ground matrix we construct doesn't have the equality here, and this means that we cannot fool SOS with this. But maybe some physics will do. But before we fix this matrix, let's go back to pseudo calibration again. Recall that we learned a candidate moment matrix M2 from pseudo calibration, but we just don't know whether M2 is PSD or not. And an idea that we try is to combine both M1 and M2. And what do we mean by that? We can write M2 as M2 equals to M1 plus M2 minus M1, and use triangle inequality to say that the smallest eigenvalue of M2 is lower bounded by the smallest eigenvalue of M1 minus lambda max of M1 minus M2. Therefore, to show that M2 is PSD, i.e. lambda mean of M2 is greater than 0, we only need to say the smallest eigenvalue of M1 is lower bounded by the largest eigenvalue of M2 minus M1. Therefore, to prove an SOS lower bound, everything boils down to proving special non-bounds for matrices of random but not IID entries. Okay, but what kinds of technique do we know to prove special non-bounds for these random matrices? We know that random matrix theory is well developed for matrices of independent entries. However, the matrices we look at here are random, but they don't have independent entries. And to bound the special non-bound of this type of matrices, people usually rely upon powerful but complicated trace method. In our work, we get rid of trace method by designing a simple low-weight machinery that achieves tighter bounds for matrices that arise in our condensing trace method. And this relies upon a crucial but simple observation that if we know that a matrix can be written as a product of matrices, for example, if Mg equals to M1 times M2 times M3, then we can also just upper bound the largest eigenvalue of Mg as the product of the special norms of individual matrices. And the takeaway here is, even though the original matrix we want to bound can be super complicated, for example, it may have correlations across entries, the matrix it can be decomposed into can be rather simple. Or maybe it's easy to get tight special non-bounds for this matrix that we decompose using off-the-shelf random matrix theory results. And let's look at a tiny example here. Let's start from a random matrix G, for example, a Gaussian matrix that we like. And let's consider the following weirdo matrix that actually comes out in a lot of SOS lower bounds works. Let's define an n squared by n squared matrix as the following. Mg is indexed by pairs of indices in n. So we let Mg of ij, kl as the product of G of ik to the 3 times G of jl. This looks a bit tricky, as this matrix clearly has a correlation across entries. But it also looks like it can be written as a product of matrices. And that turns out to be right. We can actually write Mg as a product of 4 matrices, where each entry is either a diagonal matrix, a broad diagonal matrix, or a matrix where each row or column is just a submatrix of G transpose. And therefore, we can upper bound Mg using the special non-bounds for each individual matrices. Using this simple machinery, it turns out that we can attempt tight special non-bounds for the matrix that we look at. And these special non-bounds are usually tighter than the one given by trace method previously. And this turns out to be crucial in our lower bounds for Mascot. And now let me end with a little bit discussion on future work. So we know SOS is an increasingly powerful algorithm. And in this work, we show that Degree-4 SOS failed to satisfy upper bounds for Sherrington-Kirkpatrick and Mascot on Delegate graph. So it will be a natural question to ask for higher degree. In a recent follow-up work by GJJPR, they have been able to show a degree-2 delta SOS low bound for the Sherrington-Kirkpatrick problem. However, the low bound for mass count remains open. Another question along this line is to see what happened at degree 0.1 in SOS. Does SOS certify a better bound there? Also, besides these two individual questions, we can also ask for SOS low bound for more average case problems. For example, mass independent set on sparse random graphs. Also, another major question along this line is whether we can say anything interesting about the pseudo calibration conjecture. We know pseudo calibration gives us a candidate pseudo moment matrix. However, is it true that every pseudo moment matrix coming out of that way is PSD? If the conjecture is true, we will have an automatic machinery improving SOS low bounds without going into case-by-case analysis. Thank you for your time.